Well, good evening. We're going to probably make this a pretty quick talk here. Talking about the life cycle of stars part 2, continuing from part 1. Last time in part 1 we looked at the conditions necessary for the birth of a star. What we're going to take a look at this evening is once a star is born, once it has reached its limit of contraction and it begins to fuse hydrogen, what happens then? So we're going to talk about its extended youth and then talk about what happens when old age begins setting in. So I'm going to actually start this off with a real quick video from over on YouTube, which will kind of do a really good job of summarizing how a Hertzsprung-Russell diagram works. So like you saw right there, it did a really good job of just summarizing the sorting of stars according to their brightness on the vertical axis and their temperature reversed on the horizontal axis. And so you also saw how most of the stars that were in that particular cluster were on the main sequence, which was in that from the top down to the bottom right kind of diagonal there. I'm going to jump over to the next slide here. So what we're looking at right here is actually a HR diagram, and the different tracks on here are protostars that start off with different masses. And so if you kind of look in the middle, we've got a 1 solar mass star, which would be about how much mass there is in our sun. And you can see with each of these, what's happening is they are contracting. When they're still protostars, they're contracting and getting smaller. And as they get smaller, they begin to heat up because that pressure, especially in the inner parts of the star, begin to generate heat. As pressure increases, temperature increases. And so they will continue increasing in temperature until they reach a limit. And that limit is around 12 million Kelvin in the core. And once a star reaches about 12 million Kelvin in the core, then hydrogen fusion begins. And so the star will stop contracting, and the force from that fusion will kind of resist that contraction. And once that happens, of course, it is officially a star. And it will spend once it reaches this what's called the zero age limit on the main sequence line here, it will tend to spend most of its life at about the same place. Now, what I want you to notice in this picture is that the ones that have higher masses, the numbers in the dots is about how many years it takes at that particular point before it moves on to the next. And you can see up here at the top, the higher mass stars collapse much more quickly because there's a lot more matter that's pulling them into the middle. Whereas the lower mass stars down here at the bottom, it can take a really long time for them to even begin burning. And it turns out that there's a certain what's called a critical mass. And if a developing star doesn't have at least that much mass, then it will never achieve enough pressure and a high enough temperature for it to start burning. And it'll just kind of turn into a little brown dwarf, or, some that are even smaller become planets, and never be a star at all. And that critical mass is about 0.075 the mass of our sun. Something can still be about 1/10 the mass of our sun and still be a star, but if you start getting too much smaller than that, then there's a good chance that you're not going to have enough mass there for the star to actually ever activate. Okay, so let's go on to our next slide. Okay, like I mentioned in the previous slide, once a star reaches the main sequence line, then it will spend the majority of its life there. Its brightness and its temperature will not change very much. There will be slight increases in temperature for a star, so it will move very slowly off to the left, but it's not going to move very much for the bulk of its life. So what you can see here is you've got some different spectral types of star. Our star is a spectral type G star. And spectral type G star, our star actually has somewhere around a 5,800 Kelvin surface temperature and a mass of about 1 compared to the masses on here. And so it will tend to spend somewhere, I think our star is somewhere around 12 billion years that it will tend to be on the main sequence before it moves into later stages of its life. You can see that some of these larger stars, like the type O and the type B stars, they're absolutely huge. They've got a very high surface temperature, and they will only stay on the main sequence for a very small amount of time, like 1 million, 10 million years. Now, the reason why this is important is because our star, the sun, was the mass that it was when it formed, it has been fairly stable for a very long time, and it will continue to be very stable for a long time to come. Long enough for life to develop on the planet and to continue to exist relatively consistent on the planet since it did form. So when we look at other stars where there might be planets that could support life, whether that's life for us to, study, make contact with, that's already there, whether that is a planet that could support us should we ever make our way out of our solar system to other stars, we look for stars similar to ours that are down here in like the G type or the K type, because they're more likely to have planets that have been around long enough and are in the right kind of conditions to support the development of life. Of course, stars will eventually use up their helium reserves, and as they use up their helium reserves, very interesting things start happening. We're going to take a look at the next slide to see that. So on the left here, you've got a cross-section of a star in the main sequence. Fusion is occurring in the core, where hydrogen is being fused into helium. Outside of that, you've got all the layers of the stellar atmosphere. And heat radiates out, pressure pushes light and heat back in, and you get the interesting convection cells like we saw when we studied the sun. But eventually what's going to happen is that all the hydrogen in the core is going to get fused out. And basically, we refer to that as a state of where there's just hydrogen ash, or actually helium ash is left over. Now, the sun at this point is not, or the star at this point is not hot enough to start fusing that helium. So what starts to happen is that you don't have the fusion in the core and all the pressure from that pushing out. So the star is going to begin to collapse in on itself. Not all the way. It's going to collapse a little bit. And once it collapses a little bit, there's some hydrogen that is out here, not as much as was in the core, but there's a little bit of hydrogen out here in the outer layers, and it's going to heat up enough to where it's going to start to fuse. So you start to get fusion of hydrogen outside of this core. Now, as this hydrogen out here fuses, it actually fuses faster and hotter than hydrogen that was fusing in the core before this happened. And so that heat is going to leak out to this outer envelope here, and it's going to cause it to expand. And the star is going to start getting bigger and bigger and bigger. As it expands, the material on the outside of the star, because it's expanding, it's going to start to cool. And when it cools, the color of the star is going to start to turn red. And so looking back at the previous slide again, here we have the sun. It's a yellow dwarf star. Here we have Delta Bootis. I'm sure I'm saying that wrong, but I don't care. It is a red giant that was once a smaller star like ours, but it has begun to expand and cool. And then you have this up here. Don't know if that would be Xi Cygni or Xi Cygni. And you were just able to see a little piece of it. That's actually a red supergiant, because the main sequence star that it came from was much, much more massive. It would have been one of these type O or type B stars up here. And so it burned through its hydrogen very, very quickly, because there was even more pressure on the outside. And if there's more pressure from that mass, that causes a higher temperature, and the higher temperature means that fusion's happening faster. So the really big ones burn very bright, but they burn out very quickly. And so eventually, as a star gets bigger and it gets redder, it's going to leave its position, not physically, but its position on the HR diagram, and move up to the right, and it's going to become a red giant. So you can see that happening on this HR diagram here. Here are stars that have finished burning through their hydrogen. They contract, which causes that secondary fusion to start happening in the outer layers, and then it causes it to start expanding, and the outer layers cool off. And so you can see for each of these, they're going to kind of come out a little bit. They're going to crash back up and then become bigger and bigger. And again, the dots you see here are referring to, I believe, the amount of years that it's going to take. And so you can see up here at the top, these are much smaller numbers. These are going to get very large very quickly. This star right here is the star Betelgeuse, which we have talked about several times. It is a supergiant, and it's very large, but it's also beginning to near the end of its life cycle. Here's a size comparison we've looked at before. If this right here represents the size of Earth's orbit, this right here is the current diameter of Betelgeuse. It's even bigger than the orbit of Jupiter. But Betelgeuse is, if you look at this chart, it has about 16 times the mass of our sun. And this chart does a really good job of comparing several things between Betelgeuse and our sun. The surface temperature of our sun is 5,800 Kelvin. Betelgeuse is much cooler. Its core temperature is much, much higher, though, and that's owing to all of that mass and all of that pressure. And so you've got a lot more pressure, you've got a lot more heat, and so the processes of fusion are happening much more quickly in there. It's about 46,000 times brighter than the sun. But you can also see that it has burned out so quickly, it's not going to live, it's not going to continue to sustain itself anywhere near as long as our sun. See, our sun is right here. It's actually still on the main sequence. In another 8 billion years or so, when it starts to do the same thing, it's going to have a much more gradual fade to the red giant stage. By that time, there's a really good chance that humanity will have been long gone, and we won't be around to see our sun slowly expand and engulf the inner planets as it gets bigger and it gets redder. The next time that we talk, we're going to talk about what happens to these red giants when they finally begin to die. And we will also talk about what happens to these red supergiants like Betelgeuse here when it dies, and some of the really impressive ways that it will go out with a bang. So until the next time, enjoy.